questions from 3.6? Does anybody have any questions from 3.6? Oh, okay. Well, if that's the case, we'll definitely finish with 2 sections. We definitely could finish 2 sections with time to spare if there's no 3.6 questions.
It was a really easy lesson.
It should have been pretty straightforward. There wasn't anything really tricky going on. Again, if you were good with kind of what things were going up until then, it should. Oh,
Did you do 43?
yeah, of course.
Wow. Sorry.
Wow. What was it?
43. Ah.
The reason why I don't like sections is because
So for 43, again, the directions say use logarithmic differentiation. So we want to start by doing the log of both sides. And then I'm going to use the power property of logarithms to move the exponent inside the log into a coefficient. And then we'll do the derivative of both sides. So the derivative of log y is 1 over y, dy dx. And to do the derivative of x log x requires a product rule. So I have x times the derivative of natural log x plus the natural log x times the derivative of x. So if I reduce things, I have 1 plus natural log x. And then I'll multiply both sides by y, which is x to the x. And that should be an acceptable answer. Hi, thank you. They might have also written this as 1 is the same thing as the natural log of e. So potentially they could have written this as like the log of e to the, or ex times x to the x. I don't know. This would be okay for me. Ben, you got yourself a pass here. It is. Christian, does that feel?
Yeah, I just did the.
Okay. I don't remember. I'd been a long time since I've looked at the answers. I don't know what the answer looked like, if it was the first one or the second one, but. All right. 3.7 then. So 3.7 contains no new information. It's just like, okay, here's some story problems that involve using calculus. So we're just going to do an example here and then move on about our business. Sound good? So it says the position function of a particle is given by the equation, yada, 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 where t is measured in seconds and s in meters. Find the velocity at time t. Who remembers the relationship between velocity and position? Velocity is the first derivative of position. So what would the derivative of s be? Everybody agree with that?
Yeah.
That looks good. It says, what is the velocity after 2 seconds? So that's going to be 12 minus 24 plus 9, that's -3. And that'll be 48 minus 48 plus 9, that's 9. Now, I did that arithmetic in my head, but if I had the option and I was on the AP exam, and this was a calculator active problem, this is how I would do this problem in my calculator. Because I don't want to get this wrong if I accidentally did the derivative wrong. So what I might do instead is start with that original function and type that into the y equals menu. oops, that's 9 or 6x squared. Dum-dum. There you go. And then I'm going to exit out of there. I'll press the math button then and select option number 8, which is called N derive. So this looks like the derivative notation, right?
Yeah.
I'm going to indicate that I'm going to do this derivative with respect to x. And the thing I want to differentiate is the equation I typed into y1. So I'm going to press vars, yvars, function, y1, and tell it to evaluate that derivative at 2.
-3.
So that's my -3. Now, the way the calculator is actually doing this, it's not actually taking the derivative, it's doing like an approximation. But that's why it's getting something that's very, very close, but maybe not exactly. And then I can do the same thing at, say, 4. Again, very, very close, but maybe not exact. So I can do that. And even, I should say, on the AP exam, on the calculator sections, you conceivably would run into a problem where they expect you to do to do it this way, because the problem would be really cumbersome to do the derivative by hand and then plug the value into it. Would not be maybe as simple as this one. Like if it was something with like chain and product and quotient rules all kind of running into each other together, where it's like, oh, I could do that, but it's going to be a lot of time, and maybe I don't have enough really time to be able to do that by hand. If it's a calculator section, they don't expect you to do it by hand. They would expect you to do it on the calculator, just the same way that I've done here. Everybody okay? All right. Part C says, when is the particle at rest? How do I find that out?
When it's velocity 0.
When the velocity is 0. Great. So how could I solve 3t squared minus 12t plus 9 equals 0?
Factor.
Could try factoring. What else? Quadratic formula. What else?
Completing the square.
Okay, completing the square. What else?
Favorite.
Graphing, right? Those would probably be the 4 that I would choose. If it was calculator active, graphing would be an effective method, right? I just plug that into the y equals menu and find the x-intercepts. Let's do the quadratic formula just as a reminder of what that is. What's the formula for the quadratic formula?
Minus b.
Negative
plus
b.
minus, b squared minus 4ac over 2a.
Good. So let's see, what do I get here? 144 minus 108, that's 36. Square root of that is 6. So if we add, that's 18 over 6, that's 3. If we subtract, that's 6 over 6, that's 1. Guess we should put a unit on that. Probably do the same thing here, right? Meters per second. So far, so good? Part D says, when is the particle moving forward? That is in the positive direction. So forward would mean where the velocity is positive, and backwards would be where the velocity is negative, right? How am I going to figure that out? Just did that. Let's start with the easy one. If I have access to a calculator, what can I do? Graph it. What am I looking for? where it's above and below the x-axis, right? So greater than 0 is where it would be above. Below the x-axis would be where it's less than. Everybody's okay with that? What if I don't have my calculator access, though? What if this is a no calculator problem? Well, what I would do is I'm going to construct what's called a sign diagram, because I know that this function is 0 at 1 and 3, right? Those are the only two places where the graph is 0. What I'll do then is I'll pick an x that's less than 1, an x that's between 1 and 2 or 1 and 3, and then an x that's bigger than 3. Does it matter what x I pick? No. But I'm going to be smart about it because I already know the velocity at, I should say these are t's, not x's though, right? What's the velocity when t is 2? -3, we found that earlier. What's the velocity when t is 4? 9, we did that earlier. What's the velocity when t is 0? That stuff just drops out, so it's 9. So what does that tell me? Since the only place where the graph can cross the x-axis is at 1 and 3, the graph has to be positive in those sections and can only be negative in this section.
What is that backward A?
That is the symbol that's abbreviation for the phrase "for all."
I've never seen it.
Yeah, it's a common mathematics abbreviation. I try not to let too much of that stuff trickle in until we get to like courses at this level where we have students that are like potentially taking multiple college math courses, where you'll start seeing this notation more and more and more. And I'll let this stuff kind of trickle in as we go. And anytime you see a symbol you're not really familiar with, feel free to ask. It's usually just an abbreviation for some kind of common mathematics phrase.
Okay. And then also, would these be open or closed parentheses? Or does
These,
it not matter?
no, it does. So because we're strictly saying greater than and not or equal to 0,
Okay.
those have to be
Greater than.
parentheses, right?
Yeah. Sorry.
That's okay. Yes, Giselle. Oh, okay. Very good. Does everybody feel all right with what I did there? The sign diagram is how you solve like a polynomial inequality, right? Where it's, I can't just set this greater than 0 and then solve it and just say, oh, x is greater than, 1 and greater than 3. It's like, oh, no, no, no. It doesn't work like that. Draw a sign diagram. It makes life pretty easy from there, though. Part E says draw a diagram to represent the motion of the particle. All right. So let's see. So we'll draw start doing something like this. Yes. Oh, sure.
Thank you.
And let's just make this like an s-axis here. So in the beginning, at t equals 0, the position is 0. How did I get that? I just plug 0 in for t, right? And then the particles moves forward until we get to time t equals 1, right? Because at that point, we know we're going to change direction and start moving backwards. At 1, we have 1 minus 6 plus 9, so that's position 4. So now we start moving backwards until we get to time 3. At time 3, we're at position, well, 27 minus 54 plus 27, that's 0. At which point we turn back forward and keep moving forward for the duration, right? So that's kind of like our diagram of what that particle's doing. Physics students, does this look familiar?
Yes.
This
very
kind of thing
familiar.
that you're used to doing, building a motion diagram or whatever.
It wasn't my favorite thing in physics.
I'm very good with like symbolic and theoretical, and I become much less steady when it gets to the physical world as well. So yes.
So does S have to be that like constant? Like just like is this just a line for S? Like for the diagram?
Just a line. What do you mean a line for us?
Like are you just
So well, like I moved, like I'm 4 units over, right? Like here's like 0, 1, 2, 3, 4.
Okay.
So it moved 4 over, 4 back, and then it keeps going forward. I just tried to scale it.
Oh, I was like, is that like another line that goes along with the red?
No. That's just like a scale, like an axis. That's okay.
Sorry.
No, if you're not sure what I'm doing here, like for sure ask. Even if it's like, oh yeah, that's all that. Well, oh, okay. Well, I didn't realize that's what you're doing because you didn't say it. And it's like, oh, that's fair. All right. So what we need to do now is we need to find the total distance traveled by the particle in the first 5 seconds, right? So how am I going to do that?
Is it just F of t?
You mean S of t?
Yes.
No, because unfortunately the particle is going forward and backwards sometimes. So the displacement is going to be less than the distance traveled, right? Like if I drive from my house to work and then back to my house, I didn't go 0 because part of it was going forward and part of it is going backwards. Tends up to be 0 displacement, but I definitely went and I drove for a long time, right? So we have to be careful. So we need the forwards part. So 0 to 1. And then we need the backwards distance, 1 to 3. And then we need the forwards part from 3 to 5.
So this equation that they gave to us, the S of t, is that for displacement?
Mm-hmm.
Oh, okay, got it.
Yeah, position, displacement, same
Okay,
thing. So to do that, to calculate how long I was moving forward, I'm just going to do S of 0 minus S of 1. Well, I know what that is. That's that distance right there. That's 4. And then I'll do S of 1 minus S of 3. I'm just going to do the absolute values of these things because it's a distance. I don't care whether it's positive or negative. But again, I know what that is. That's just that distance, which again, going from 4 to 0, well, that's just 4. And then I need the distance from S of 3 to S of 5. Well, I know at S of 3, we're at 0, right? But S of 5, I actually need to calculate. Let's go and do that real quick. So I have 125 minus 150 plus 45 is 20. So my total distance is 28, well, and I guess meters, right, was the unit for the length for S was given to. That's okay.
Why the absolute value?
Because it's talking about the total distance traveled. So distances are always positive. So I didn't want to have to muck around with like, oh, should I be subtracting this one from this one? Because sometimes we're going forward. Take the absolute value of all of it, and I just have to subtract the 2, and I don't have to muck around with like, which order should I do the subtraction? Like I don't have to be picky. I can just be really sloppy and just go.
Okay.
Right? Because if I'm going from like 3 to 5, if I do 3 minus 5, the distance is -2, but distance can't be negative. As opposed to if I went subtracted 5 from 3, I should get positive. It's just so I didn't have to think about whether I should be, which one I should be subtracting from which one. I just subtract and then the absolute value and just be done with it. You know what I'm saying?
Yes.
G is next, right? Find the acceleration at time t and after 4 seconds. So what is our acceleration going to be? The second derivative position. So if our first derivative was 3t squared minus 12t plus 9, what's the second derivative?
Wait, which one's the derivative? I'm sorry. Of 3t squared minus 12.
Velocity is the first derivative.
Okay, 6t minus 12.
Yep. That was easy. And then at 4 seconds, what do we get here? 12. I should put a unit probably on that, meters per second squared. And then we ask for graph the position, velocity, and acceleration functions for 0 to 5. Okay. And let's see here. Make some space. So 1, 2, 3, 4, 5. And then this could get pretty high. Let's say 4, 8, 12, 16, 20. I should probably do the same thing going down. Negative 4, 8, 12, 16, 20. All right, we'll do the acceleration first. We'll do that in red. So I know at 0, what is the acceleration? Negative 12, right? So like down here. And at 4, we're positive 12, so that's 4, 8, 12. So I can just kind of connect those dots. That ought to do us, right? Everybody feel good there? We'll do the velocity in blue. I'm going to try to get away without having to do a whole lot because I'm going to use things I already know. So I know the velocity is 0 at 3 and 1. I know the velocity was 9 at 0, negative 3 at 2, and 9 at 4. So 9 at 0, negative 3 at 2, and then 9 again at 4, and at 5 it was 20. So that's probably enough to get a good parabola. Everybody feel good there? And then for my position, let's see here. I know that at 0, we're at time 0, position was 0, and then 1 is 4, and 3 is 0. So at 0, 0, 1, 0. Oh, I'm sorry, 1, 4. 3, 0. And then at 4, the position was, well, the position was 20 at 4. That's, oops, that was in the wrong spot then. What is the velocity at 5? I guess we didn't calculate that anywhere, did we? Guess we just do it real quick. 24. So that would be here. So that's good. All right. And then at 5, our position is 20 at 5, excuse me. At 4, do we have a position? We don't, but I guess it doesn't really matter. So it's going to look like something like that. Now, how did I know that when I graphed that, to not dip that position function below the x-axis at time 3? Well, because I went forward 4, backwards 4, and then forward the entire time after, right? So at no point could I ever had negative position, because I only moved backwards 4 units, and that was only after already moving forward 4 units. Does that feel okay on how I sketched that thing? Is that the last thing I asked to do here? No. When is the particle speeding up, slowing down? Okay. So how do I figure that out? So I need to look at where the acceleration is positive or negative. Again, I have that right here from the graph, right? Just when t is less than 2, it's negative, and when it's greater than 2, it's positive. How else could I have done that if I didn't draw the graph? The sign diagram, just like I did before. First, I solved that equal to 0. 6t minus 12 equal to 0. That's 2. Pick a value on either side, and that'll show me. But that's 0 to 2, and that is 2 to positive infinity. So if I draw this now, okay, so our acceleration is slowing down all the way to 2, and then it's speeding up after that, right? And then if we look at our velocity, oops, I know from 0 to 1, we're going forward, and then after 3, we're going forward. But between 1 and 3, we're going backwards, right? Yes, Chanel?
Oh, wait, so what's the difference between the yellow and green and purple and
I'm just getting ready to color code it for us.
oh, sorry.
So the green and red, or the green and yellow, are slowing down, speeding up. The pink and purple are moving forward and backwards.
Wait, how did you solve for pink and purple? Was that like
Just what we did back here, right?
okay? Okay, sorry.
That's okay. Okay. All right. So this is always the part that I have screw up. So let me just be careful here for a moment. Okay. So the place where we are speeding up is when the velocity and acceleration are the same sign. Right? If you're moving backwards and your acceleration is negative, you're increasing your speed in the backwards direction. If your acceleration is positive and you're moving forward, you're increasing your speed in the positive direction, right? So that happens here, where we're moving forwards and speeding up. And that happens here, where we're moving backward and slowing down. Or, I'm sorry, moving backwards and accelerating in the negative direction, right? And then the slowing down is going to be the opposite pieces. Okay. So speeding up. Just think about like you're in your car. You put your car in reverse. You step on the gas. You're going backwards and your speed is increasing, right? You're accelerating backwards. So that's speeding up. You hit your brake. Now your acceleration is, slowing down, right? Or your acceleration is decreasing. So it's going in the opposite direction. So the acceleration is now forward. You're still moving backwards though, until you get, so you're slowing down till you stop, put your car in drive, you push down on the gas pedal, you start moving forward and you're accelerating forward. Your car is speeding up. You come up to a stop sign, you push the brake down, car's acceleration is decreasing. It's now in the opposite direction. It's negative, but you're still moving forward. Your car is slowing down. Right? That's always the thing I have to talk through to my head to make sure I don't screw that up. It's just like, think back to driving my car from, backing out of my driveway to going to the stop sign. And I can usually get it right. But if I don't think about it, I just screw that up for whatever reason. Those of you that have been in physics more recently than I, maybe that's a little bit easier. So that was 3-7. That was it. We just did one example. All the other 3-7 examples are similar to this. 3-10 is super easy. Do you want to do it or no? Okay. So the options are stay or go. Stay means, or stop or go. Okay. Show of hand stops. And then show of hand goes. Okay. So stops 1.